Okay, I want to talk about another very simple way in which you can characterize flow units. I showed you earlier another way to do this, where you just kind of looked at developed ranges of properties and gave those ranges different names and mapped them and things like that. Well, I want to show you another method here that doesn't require as much geology, I'm sorry to say, but it works quite well. It's an old method, but has been used for a long time to do flow unit characterization and, in particular, correlation between different wells. So the method here is the Gunter method. Okay, it's called the Gunter method after a guy by the name of Gary Gunter, who worked for a company called Amoco that no longer exists. It's now part of BP. But he developed this technique and used it in Amoco for many years as a very simple reservoir characterization technique. Again, if you don't have much seismic data, or your seismic data is not very good, then this is another technique you can use. There are two parameters that you calculate. One is called the cumulative flow capacity, and that is the product of the permeability times the thickness. And the other parameter is cumulative storage capacity, which is the product of porosity times thickness. So really there's only three parameters that you use, no geology or anything like that. The three parameters being, two parameters, cumulative flow capacity and cumulative storage capacity. And the properties that you use, the three properties, are permeability, thickness, and porosity. So that's all you need to know to use this method. And the procedure, which I'm going to show you in a minute, is just to make a cross plot of these two properties. And always your plot begins in the lower left corner. That's not so important here, but let me show you how this works. This actually, Gary Gunter was a petroleum engineer, still is, and he developed this technique, I think because he didn't like all that geology or something, I don't know. But at any rate, this is just a hypothetical example. If you have 5 feet, you have let's say you have a core plug every 1 foot for a total of 5 feet. So we'll say from 1801 to 1805 feet. So you take a core plug at each one of those feet, and you measure the porosity. So 15%, 20, 15, 10, and 5. And so you then calculate the porosity times the thickness between measurement points. So in this case, you're 1 foot apart in each of your measurement points. So you're 1 foot there. So you multiply porosity times the 1 foot thickness, and you get a number. Okay? And you can total up that number, and you'll end up with something. In this case, by hypothetical example, you get 0.65. Now you do the same for the permeability. You get a permeability measurement for each of those 1 foot, and you then multiply that permeability by the thickness, which is 1 foot again, And so you get a numerical value here, and you can sum that up to 47 permeability feet, or permeability thickness if you want, and this is porosity thickness. Well, that's step one in this process. Let's go to step two. What you want to do now is find out for every one of these 1 foot intervals, what is the fraction of porosity thickness and the fraction of the total permeability thickness. And that's what step two is. So what you do is you take your, let's look at porosity first. So you take your 0.15 for this interval, and you divide that by the total porosity, porosity thickness, 0.65, and you get this number. And you do that for all 5, and when you total them up, since it's a fraction of a total, it equals 1 or 100% is your total fraction, or your total porosity thickness. And each one of these feet, this is 0.23 of your fractional porosity thickness, 0.31, and so on. And you do the same thing for the permeability. Multiply the permeability, like for the first example, it's 10 millidarcies, divided by the total, 47, so it's fractional, comes out to 0.21, and you do that for all 5, and that'll equal 1. So that's step two, all very simple mathematics, like us geologists like. And then step three is that's when you determine your cumulative storage capacity and your cumulative flow capacity. So how you do that is you take your first measurement of fractional porosity thickness is 0.23. You put that there. You then add up, you sum up this one, the 0.23 and the 0.31. You get 0.54. You add this one, 0.23, gives you 0.77. Add this one, add this one, and this one gives you 0.9, and then gives you a 1.0 again. And you do the same thing, cumulative flow capacity. Your flow capacity is going to be a function of your permeability, so it's permeability times thickness, as opposed to your storage capacity, which is a function of your porosity, so porosity times thickness. And then you just make a cross plot of these two parameters. Simple as that. Kind of went ahead of myself here, but okay, so here's the plot for those values. Now, here's the values for cumulative storage capacity, and here's the values for cumulative flow capacity. So, cumulative storage capacity on the horizontal axis, cumulative flow capacity on the vertical axis. And wherever you have a straight line segment like that, that defines a flow unit, one flow unit. So in this particular case, with these measurements and these calculations, we end up with 2 flow units, and the slopes of the curves are different. So if you have a number of wells where you have core plug information and just the bed thickness, if you can make an estimate of that from the well logs, then you can do this sort of flow unit characterization without inputting any geology at all. Well, quite often real reservoirs are more complex than this hypothetical example. So here's one example here where we actually, we had 11 flow units that we calculated by that method that I showed. And you can see here's flow unit 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, a little one at top, 11. So in other words, where you have a change in slope of your curve, that defines a separate flow unit. So we have a boundary of flow units right here, for example. We have another boundary down here. We have a boundary there. We have a boundary there. Another boundary there. Another one there. Another one there. Another one there. So, and one more near the top. So we've got 11 flow units now that we've been able to determine by this method. So all you need is the core plug depth, your porosity, your permeability, and your, well, you want to get the thickness as well. So you can make those calculations. Now, we've used this a number of times in a number of different fields and found it to be quite effective. And what we find, let's see, for example, I've highlighted here your best flow units. This is going to be your best flow unit number 4. See, that's this one here with the steepest slope. Okay? Flow unit number 6 is your second best. And see, that's got a relatively steep slope as well. Flow unit number 9 is very large, and see the steep slope. So that gives you an idea of how good these zones are going to be relative to flow capacity and storage capacity in your reservoir. So it's a very simple technique to use. We use Excel spreadsheets to do the calculation, and very effective. Let's see. Most of you are engineers, so I think what I'm going to do is skip this section on capillary pressure, assuming everybody understands capillary pressures, those of you who are engineers anyway, which are most of you. So I'm going to skip that. That's kind of a lengthy, boring topic. So let me move on. And that's all of my reservoir quality chapter. If somebody wants me to do the cap pressure, I can, but probably you guys know about that. So what I'd like to do to finish off the day is to get started now on what I guess is the most important type of reservoir for you all, and that's the fluvial and shallow marine reservoirs. It's a very long subject. I've put a lot of material into it, and so it'll take us into tomorrow morning at any rate. So this is Unit 3. If you're following along on your computer, this is Unit 3. And what we're looking at here is a fluvial system like this. And fluvial systems are actually, I'm sure as you know, are quite complex. Some are relative, when you have a very high net sand fluvial reservoir, it's relatively easy to develop. because you've got good connectivity and you can have widely spaced wells. But when you have other types of fluvial reservoirs, they can be extremely complex and very difficult to develop. You need a lot of closely spaced wells, horizontal wells are good, and things like that. So at any rate, we're going to go down the profile here. This would be what we would call a braided, well, there's an alluvial fan up here. And then this would be a braided river deposit and a meandering river deposit down to here. And then you get to the shoreline and you get your connectivity of shoreline sands, or if you've got a major river, you get a delta system out here. So, fluvial stratigraphy and reservoirs. Really 4 different types that we can define, shown here. Alluvial fans that come off the mountain fronts. They're normally deposited very rapidly from a river kind of coming out of the mountains onto a lowland area. You get rapid decrease in flow velocity, so your sediments are deposited quickly when you get to the base of the mountain, and they build outward in a fan-shaped body like you see here. Now, because they're usually the product of high energy flows, they often are coarse-grained, but they can also be quite variable. And you can have mud in the system. There can be permeability barriers or baffles or things like that. You have then, as we move down, well, as we move, let's see, let me go back. What I'm doing, I'm moving from alluvial fan now to braided to meandering. So moving down, braided river deposit. We often call these low sinuosity because the sinuosity is very low. In meandering rivers, you get very high sinuosity, we call it. But braided rivers, because they are the product of relatively high flow velocities, the deposit is usually relatively coarse-grained, often no mud or very little mud in the system, and usually not too many barriers to fluid flow. So coarse-grained, here's a picture of one here. You have, at any one time, you might have one channel active, or in this case, maybe 2 channels active, and with time, these channels will migrate back and forth to build up this braided river system that also kind of often takes a kind of a fan-like shape, but relatively coarse-grained, high-energy deposits. Now we get up and so they're relatively easy to develop. Now what becomes very difficult, I've got a lot of material I've brought on this, is these high sinuosity meandering rivers. And you can see the big meander loop here, going around like that. Your reservoirs are generally not in the channel, but they're adjacent to the channel as point bar deposits. Like this here on the inside bends of these meander loops. You find nice sand there, nice sand there, nice sand there, nice sand there. The problem with these types of reservoirs is the channel itself. Those channels are only temporary, and at some point in most of these channels, the channel migrates, it leaves its banks, migrates somewhere else, and it leaves kind of a quiet water environment here, a lake. We call them oxbow lakes, and those lakes fill up with mud. And when they fill up with mud, that mud forms the permeability barrier. It's kind of like a vertical, we call them mud plugs, And it can separate a sand body here from a sand body there and a sand body there. And your trick as an engineer or a geologist is to figure out where to drill your wells, because each one of these sand bodies, these point bar sand bodies, may be isolated from the next one by these mud plugs. And so you have to drill a lot of wells, or you may try to drill horizontal wells to get through those mud plugs. And I'll show you pictures of all of this. And then kind of intermediate between meandering and braided is what we call anastomos in the river. I'm not going to talk much about those. So at any rate, here's kind of the breakdown in somewhat more detail, where you've got a proximal zone up here, where you might have a braid plain, braided river system here, going down into a floodplain, where you get floodplain and meandering rivers down in this area. And maybe then some little sheet sands that may come out at the river mouth as river mouth bars or something like that. Here's a picture of a nice fan-shaped alluvial fan right there. Coarse grained, so on. So you can break down these intervals into proximal versus proximal, medial, and distal, depending upon how far away you are from the source. And generally speaking, as you go away, further away from the source area of the sediments, your grain size becomes finer and finer grain, because coarser material gets deposited up dip, leaving finer and finer grain material remaining in the flow to be later deposited down dip. So braided, let me give you an example of braided river deposits and reservoirs. There are some very good ones. I don't know if you have any of those here or not, but in Bolivia. But here's that picture again. And here's a close-up of an active a small channel with water in it. And then you've got these bars that are inside the channel, and you can see perhaps very coarse grain, gravelly almost. If you start digging around on these, you find you find bars sometimes that are made of sand. They can occur on, say, these parts of the system. And here's just an example, and another example where a sand body was, they used a shovel to get a vertical section, and it's very sandy, nice, well sorted, and so on. So again, high energy flows. You don't often get a lot of mud in these braided river deposits. More of the mud comes in the meandering river deposits. So a cartoon, here's one where we go from proximal down to middle and down to distal down here. Probably can't see that. The distal down in there. So proximal, medial, distal, decrease in grain size as you go down the dip. So your reservoir properties are going to change. One thing that's the most obvious change you're going to have is in permeability, because you're changing the grain size. So the permeability that you have up here in the proximal is not going to be the same permeability that you get down here in the distal section. And you may get some floodplain shales in between these rivers, but generally these high energy flows, you don't get a whole lot of floodplain shading material. Well, here's just a typical picture of an outcrop of a braided river deposit, and you can see just looking at that, it's extremely sandy. Very little mud at all in this system. There might be a few little mud drapes. I think here's one right there. But overall, about 95% net sand in this particular interval. And it's typical of a braided river deposit. Be coarse-grained sand, maybe pebbly sand, some conglomerate, and so on. In the subsurface, this one, by the way, in the subsurface is a reservoir, a very good reservoir in the Rocky Mountains of the U.S. In the subsurface, you might have something like this. Here's some core from this sandstone right there, that interval right there, and pictures of the core. And you can see a couple of things here. One is relatively coarse grained. These are little pebbles right in here. Pebble bed, so relatively coarse grained. You can see some bedding planes. There's a bedding plane right here. There's another one here with a little bit of shale on top. And you can see on your, this is a gamma ray log, and so you get a very low gamma ray response because there's very little to no clay at all, or shale, in this particular stratigraphic interval. So looking at individual pieces of this core, this might be, this is a pebbly sandstone from a braided river deposit. Here's a poorly sorted quartz pebble conglomerate. These are some thin coal beds that you sometimes get with the associated floodplain. And then here's a medium grain braided river sandstone. That's this one in here. So coarse grain, you can anticipate, unless there's a lot of clay in there, which there doesn't seem to be, you can anticipate good permeability and porosity. Now, one of the other features that you can see is the red color, and that is due to oxidation, usually at the surface before you get burial, because these sediments are exposed to air. They will become oxidized, but also in the shallow subsurface, where you might have a lot of iron in subsurface fluids, and that iron will precipitate out to give you that reddish color as well. Quite a few of the red-colored sandstones are fluvial. Also, if you have a lot of feldspar, feldspar grains tend to be pinkish or reddish pink, and they can impart that color as well. So those would be what maybe typical rock type look like with the corresponding well log. Just to point out again that there's very little shale in these rocks, in these reservoirs. Braided fluvial channel fill comprises almost all of this. You got a little shale break in here, a little of what they call the floodplain facies, a little bit here, and all of the rest of that is nice. In this particular example, this is an outcrop example that was drawn to scale, and in this area it's almost all maybe 90% net sand, and only a couple of places where you've got some lenses of shale. And in these sort of systems where you get these lenses of shale, they really are not flow barriers or baffles to fluid flow. The reservoir fluids can flow around these very nicely, so they don't really cause you much of a problem. Well, this jumps a little bit ahead of that. I show you a plot here of porosity, excuse me, not porosity, vertical permeability and horizontal permeability. And what I wanted you to see here is the best permeability is right up here at the top, where you have your highest vertical and horizontal permeability. Your meandering facies tend to have lower permeability. And then again, the braided river facies occurs up in here. Now I'll finish up today with just a description of one of the world's first-class braided river type reservoir, and that's on the north slope of Alaska, the state of Alaska in the U.S. Here's a picture, a map view of the reservoir. You have a gas cap. You have a gas cap here. You've got a big unconformity surface right there. And you've got an oil rim that's shown in green. And then your water leg here is shown in blue. If you look at the vertical stratigraphy, it goes something like this. Here's a cross-section of 5 wells. That cross-section kind of goes across like this. And what you see here is in blue are what is called distal braided river facies. In orange is middle braided river facies. So distal to middle, there's a difference here. Way down low in the reservoir, you actually have some marine delta front deposits that I'll talk about later. But basically, you have a lot of the distal braided river deposits shown in blue, and as you go further up, you start to get thicker medial braided river deposits. And then you're capped with another distal one. Well, your porosity and your permeability is going to be affected by these differences in depositional environment, which gave you differences in grain size. So just to look at this, let's just look at this plot here of porosity versus horizontal permeability, and you can see that difference. The middle braided stream deposit occurs up here, kind of in a zone like that. The mid to distal is here, and the distal braided river deposit occurs down with lower permeability. Not that much change in porosity again, but lower permeability for sure. So you're going to get a layering or stratification of your permeability in this reservoir. Even though the porosity and permeability are very high in absolute numbers, porosity from 15 to 30%, permeability, well, from 10 millidarcies, but you go all the way up to 10,000 millidarcies, and in the middle braided river facies. Well, that's a good place to quit for the day. I I'm going to spend a lot of time tomorrow morning on fluvial meandering river